Hello and welcome back to the third day of this online course on advances in remote sensing and remote sensing techniques for geological applications. Today we proceed with the lecture called Advances of Remote Sensing Applications, Remote Sensing Techniques in Geological Hazards with special emphasis on landslides. So we are going to elaborate upon landslides today, and I will touch upon slightly upon other geological hazards as well. So we need to understand that what are the natural disaster as such is available today. What happens very frequently: cyclone, tsunami, earthquake, flood, landslides, avalanches. These are all natural disasters, natural hazards. And apart from that, there are some man-made, anthropogenic, or we call it industrial hazards as well. But we are not will not talk about them today. Today we will focus only upon the landslides, and the nodal agency, all of us has to know that the nodal agency for this in this country is Geological Society of India under the Ministry of Mines for landslides. There are several satellites available. Some are, all polar satellites who are continuously monitoring land pieces, and wherever the vulnerability within the vulnerability zone, if something happens, it is well detected by our satellite sensors. Before going into detail of the satellite sensing, we just first need to understand what are the different definitions related to this topic. Hazard is an event of occurrence that has potential for causing injury to life and damage to property or the environment. Disaster can be defined as the occurrence due to natural causes or otherwise which result in large scale death, imminent possibility of deaths, etc., etc. But we need to very clearly understand these three terms: vulnerability, susceptibility, and risk. Vulnerability of an area is determined by the capacity of the social, physical, and the economic structures to withstand that. Susceptibility is basically that deals with the qualitative factors. Suppose we want to understand susceptibility of landslide in an area, that will consider the rock type, the structures, the lineament density, drainage density, soil type, all these which can contribute to the landslide occurrence. All these taken together gets me what is called susceptibility. But vulnerability is element specific. What I mean by element is that in that area where the villages are located, how many cattle sheds are there, croplands where they are there, or suppose how the road goes. So all these which are at stake will be one element. So if I put all these elements together and make a map out of it, and give some weights to these elements, and ask the software to classify, so that's how the vulnerability map will be produced. Similarly, susceptibility is basically all the causative or the conditioning factors, we call it. If we consider both susceptibility and vulnerability, we get what is called risk map of the area. So risk map, each pixel of the risk map will have a vulnerability value and will have a susceptibility value. This is what we have described the other day also. Different types of landslides. I will not spend much time on that, but basically it's to understand that landslide is a broad umbrella term, and within this umbrella there are these 15 or 16 types of landslides are there. So we now onwards we will not call that landslide has happened. We can call it a debris flow has happened, a rock fall, a rock topple, what particularly it is. So basically, if the rock falls due to under the influence of gravity, loose boulders of rock, suppose, so that is basically called the rock fall. And topple has to happen along the discontinuity plane. So there will be a discontinuity plane or weak plane. Along that, the rock toppling happens. And the sensitive slides are two types: rotational and translational. Translational slides where the failure surface is a planar one, and rotational is where it is curved one. Then spread, flow, and complex. Spreads are obviously where the water content is more, and flows are that simply means that something is flowing. So obviously my mud flow or earth flow is quite common. Rock as such do not flow. So that's how flow means lot of water is there. Any landslide that is naturally occurring in nature, generally, I mean the bigger landslides especially, they will have they will be of more than one type of landslide listed here. So maybe at the beginning they behave like a rock topple, a rock fall, and at the end they will be categorized as debris flow. something like that. So there is a complexity. So more than two or more members are involved in a particular big landslide, then they will be called complexes. Now, understanding of the landslides, we have to go by the stages. What are the stages involved? First is inventory. So anything we related to we were related to do using GIS technology or satellite based technology. First we want to make a inventory map. Inventory nothing but the polygons that are available. They denote the active landslide polygons on surface. So they basically we are dealing with the monitoring and the assessment stage. Then the vulnerability stage. Vulnerability, I told you that it is basically the elements at stake. So all the elements, their weightages taken together give me the vulnerability map. Susceptibility is nothing but the assessment again, but susceptibility we take care of different conditioning factors, rock type, structure, lineament, drainage, all taken together. Then coming to the risk onwards, basically the mitigation starts. So up till this it was only assessment. Now from risk onwards the mitigation part really starts. Modeling, that in the high risk areas modeling is supposed to be done, but that really entails about the mitigation. So there is no assessment as such involved. Now this will be the end product of any kind of hazard donation map, where we see that the different land pieces has been categorized into the severe to very low classes, and we get different zones out of this. From this we can make out spatially how important an area is with respect to landslide hazard. But before making this, we need to understand what are the thematic layers, what are the factors that are to be those are to be considered. So first, for making inventory, you can simply go by taking the polygons that is available from the images available on Google Earth platform. We see the active landslides. We have discussed how to identify an active landslide the other day. It's basically brighter tones, arcuate shape, and then there is a change in pattern and association in terms of slope, in terms of drainage, in terms of NDVI vegetation. So all these will basically tell us about how an active landslide looks like, and how it is to be detected on simple images available on Google Earth. So we have to take pre-image, we can take post images, and then compare. We can see that how much the active landslide polygon is increasing, decreasing. So that's how we make landslide inventory. Next, we go to the vulnerability mapping stage, where all my elements which are at stake, settlement and road, agriculture, these three we have taken together, but it's up to the operator. They can take more or they can take less. So they are adding these, we gets me the vulnerability. And for sustainability, we have slope, aspect, relative, geophology, structure, stream, land use, all these 12, 13 layers. We can add something into this, or we can remove any of these which we think that they are not that important for, especially for this area. So it's up to the operator, but there comes the subjectivity. You have to be very clear that what we are doing with the thematic layers. If we are adding some layers or deleting something, there has to be a reason behind this. It can be simply subjective otherwise. Next, the last stage will be the modeling part, where we go about for modeling we can do predictive and post facto as well. So generally at the starting we do the post facto one. So we know that a debris flow has happened or a landslide has happened. How it has happened, naturally, spatially, we can easily make out. And then we run our models and we see that whether the models follow the exact path as happened in nature. So if it happens to be the same, then no, like this we model several post facto debris flows or landslide, and then we gain experience to do a predictive modeling where the landslide really didn't happen. It's yet to happen, but if it happens, how it will happen, that is basically something that we can get from modeling aspects, modeling part. So this is what I have been discussing. We have, suppose, these 5, 5, 10 layers available conditioning factors. All these layers will be called a thematic layer. So they are nothing but the causative or the conditioning factors. So each of these layers basically will have subclasses within that. Suppose we take the slope class, and within this slope class I have 0 to 90 degree slope. If I have a equal interval, and then with 6 divisions there will be boundary at every 15 degrees. So 0 to 15 degrees is a class, 15 to 30 degrees is a class, 13 to 45 degrees another class, like that we reach 90 degree. So all my slope that is available there, they will be classified into these 6 categories. And similarly we have different classes for aspect, different for distance to stream, vegetation, soil depth, lineament, fall distance. So each of these thematic layers will have 4, 5, 6 number of classes with it. Now if we juxtapose each of these thematic maps on our landslide polygon map, what is happening? We are basically trying to understand what a particular role, if a particular class has some role in occurrence of landslides, influence in occurrence of landslides. Suppose slope class, we are crossing it with the landslide polygon, active landslide polygon that is naturally available on surface. We can see it, we have physically verified that. So slope crossed with landslide polygon, the resultant map, what it gives, each pixel in this map gives me information about a particular slope value in degree, comma, landslide yes or no, bracket close. So that's what. So now so if we know for each pixel if a landslide is present or no, so in the whole area wherever landslide is present, in which slope class, which particular slope class they are falling, that we can understand, and from this we can have an idea that which are the slope classes, or which of the slope class, any particular class suppose, contains more number of landslide polygons. It simply means that that particular class has to do something with landslide occurrence, or in other words we can say that they are responsible for landslide happening. So that's how. Similarly for other layers also we cross with the landslide inventory. Mind it, landslide inventory is something that we have started our work with. So each of these layer crossed with landslide inventory gives me the classes or the subclasses who are important for landslide occurrence, understanding of their influence in landslide occurrence. So now that's how we get all cross product from each of these thematic layers, each of these conditioning factors. So I jot it down here. There are suppose 10 layers like that. We can further put weights to this, and if we put weights, the weights can be put here based on the operator's field experience, or we can simply, if we are not aware of the area, we can simply play with the mathematics statistics, and we can ask the software, we can ask the algorithm to give us certain weights. One thing is that we can priorly have some weights in our mind, so that is okay, we can put them, or we can apply the algorithm, especially when we are not acquainted with the area. So we ask the software, you please come with the weightages for each of these classes in each of these layer. Mind it, if we have the weights assigned to each of the classes in each of these thematic layers, so basically we are trying to understand, suppose we have 10 conditioning factors, 10 thematic layers, and each of that layer contains 5 average your classes. So that means 50 weights is something that we are going to derive from the software, derive from the algorithm. Now these 50 weights, how I play with this, so that's basically the game involved in sustainability. So simply suppose we get different weights, and then similar weights, similar high weights, suppose high weights means they have a direct relation with the landslide occurrence, or that's how they are influential in terms of landslide incidents, landslide occurrences. So if they occur together, wherever they occur together, we give a red color, and then from this congregation of the red zone we can understand this very high susceptibility zone. Similarly very low, generally very red to green, and dark green is the color concept we use here. Similarly for vulnerability we get similar classified map. For vulnerability we have taken here the built up area, the road, and the agriculture. If we take these together, add this up, and then further we can put weights, because suppose I am well aware of the area, I know that roads are mostly important in this area. So roads are something we put more weight with, and less to build up area and agriculture. You can add on to several other important elements if you think like, or you can delete also. So that's how we get vulnerability map. Please understand the vulnerability map shows where your all roads are in red. So that means specifically the operator has given more weight to the road. Now if I cross this sustainability and vulnerability together, we get what is called risk map here. That is, we get it here. Now apart from risk, especially for landslide hazard, we have, or any other natural disaster, we need to understand that for considering, for calculation of risk of an area, are these two terms sufficient? So vulnerability, susceptibility. Apart from that, is there anything else that we are missing? Yes, there are. There are certain factors that we are not considering here. What are those? First is that the factor of safety. What factor of safety is? Factor of safety basically is resisting forces by the driving forces. So that basically tells how competent, how strong my buildings are. The buildings are made up of RCC, reinforced concrete, or they are simple kacha house, pakka house, like that. So we know the competence of the strength of the area. Same vulnerability, same susceptibility, but if the building is strong enough to withstand a landslide or a seismic wave, then the risk has to be low. But anyway, that factor of safety part we are not as such is considering here. Or it can be, suppose, the exposure. By exposure I mean that who at all are exposed there. Okay, we are considering the building footprints, village location, roads, agriculture land, etc. in vulnerability. But what about the quality? So who are the people they are involved there? So any hazard, suppose a typhoon happening here, mainland India, and a typhoon happening in somewhere in deep Andaman, Sentinelese Island, where the tribes are there. So the effect on the tribes and effect on us, the mainland man, will not be similar. So the ethnic group who are exposed to that, so that's why exposure is important. Who are exposed to a particular degree of hazard matters. So that also has to be taken care in risk mat, but we're not considering that. So the apart from these 2-3 factors which we are not considering, if I consider only vulnerability and susceptibility, that is also sufficient enough to get an overview or crude idea of what can be the risk of in this case particularly landslides. Right, so this is how we start our journey in landslide hazard generation. First layer, we have to make the inventory. Inventories are active polygons that is present on the on any satellite image, or you get it from the field, verify it from the field. But how to identify a landslide on a natural color composite or false color composite? It's quite simple. As I have told you, first you have to look for, if a fresh landslide has happened, obviously there will be that rock exposed will be of brighter tones. The shape of the I mean the surface will be, where from the landslide initiates, it will be always be a curve like shape. It's not a straight line, so there will be curved shape. So look for these curved shapes. Then third point will be your there will be change in pattern or association of slope. So slope was coming like this, and then a landslide happens, so slope depends like that. So there will be change in pattern or association of slope. There can be change pattern association of drainages. So one particular drainage was coming, now vanished, or drainage was earlier not there, now due to the landslide drainage has came up with. So the land piece now has drainages which earlier was absent. Or can be change in pattern or association of NDVI, the vegetation part. So if vegetation, particular type of vegetation was there, and then landslide happened, so that will be wiped off. But again, after some time, once the landslide is stable, then there will be different type of vegetation may come up from this. So one particular patch, you see, it's a of different type of vegetation, and ambient surroundings are of completely different. So that basically may indicate that it may belong to a old landslide zone or landslide scars. So that's how we identify the landslides on active landslides on satellite images. So this is how on 3D you see how the landslide polygons has been draped over. Now coming to the vulnerability map, we need this kind of images where pre and post images we have compared. So buildings or villages were there, now they are not there. So that's how we, for the road also, the beauty of the road with especially in hilly areas is that one single road goes like this. So something happens at the top and it comes under the influence of gravity. Same road is blocked at several places due to one particular landslide only. And then be agricultural field damage. The agricultural field was there, and then now it has been completely damaged due to your landslide deposits coming down. So if I take these layers together, settlement, road and agriculture land, if we take this together, we get a vulnerability map like this. We have put more weights to the road, so that's how they are red in color. Now for the thematic layers sustainability mapping, what do we have to do? We have several conditioning factors. Yes, we have. I have told you that within these, each of these, there are several classes like this. 5, 6 classes in each are involved, and each of these classes are important in terms of landslide occurrence. So this is simply an graph that shows the weights that we have got. One method is associated. We have conducted by in this particular exercise is information value. So information value is nothing but the weights that has been assigned statistically to each of these classes in each of these thematic layers. So that's how to total all these bars. Each of these bars represent one class, and wherever they are positive value, they simply indicate that they are more influential in terms of landslide occurrence. If they are negative, that means they are not at all influential. So if we get the each pixel of this gets one value for the sustainability map, that means they have one value for lithology, one for structure, one for geomorphology, one for lineament, and then finally if we take all these 13 layers, so each pixel basically contains information about this, and whenever the information value goes high, we make it in red color. So that's how all red zones are indicative of high hazard zones. So that means that landslide has been happening here, or if not happened, the near future it will happen soon. So that's how we have come up with till now like this. Agriculture built up and road buffer gives me vulnerability map. This crossed with sustainability gives me the risk. Side by side it looks like this: vulnerability, sustainability and risk. So for each of these each pixel in the risk map, we have a value in sustainability, we have a value vulnerability. So if I cross these two, we get risk. We get landslide sustainability map from Yamunotri. We get sustainability map from Kedarnath area. This is obviously post 2013 disaster. Coming to the second part of this lecture, where a flow modeling we can attempt. So what a debris flow is, debris flow or mark flow, whatever it is basically a fast moving liquefied landslide, and then it's a mixed unconsolidated water and debris. Appearance is like flowing concrete, and shape is like a torrent, so it's a sharp crested torrent. And then the triggering mechanism for a debris flow can be cloud burst, can be earthquake, reservoir drawdown, etc. Okay. So for debris flow, generally it is meant that it's not simply rock chunks and water coming down, but the original bedding or lamination that was available with the debris, that also is largely destroyed. So why it is important? Because we have to understand where we are standing. We are in the with all surrounded us is the Himalayan fault or thrust zone system, where every now and then it is prone to the seismicity effects, and landslides are quite common in this place. So that's why we need to model a flow. Why to model a flow? Because till now we have understood that how to make a hazard donation map, but the analysis, but the present studies on landslide hazard basically has gone beyond this, and everybody now adopts a numerical model because it is objective. So we have seen that there is subjectivity in hazard donation map, but as because this is done by numerical methods, mathematics based one, so that has to be objective. Simulation of natural events of national importance that we have to do, and unearthing the causative factors. The causative factors as such can be unearthed. Prediction of extent of runout zone in future potential flow, we can do that, and strengthening of landslide hazard mitigation measures. So that ultimately helps in mitigation measures. We have seen there are 5 events here. We have done post-fact analysis, and many of the few of them are for predictive modeling as well. What basically we get from this software, from this modeling, we get the height, the velocity, momentum, and the pressure. These 4 characters is something that we get from the model. And what will be the input for this? Before that, let me show you how it looks like. So debris flow starts from this place, is a source area, it flows like this and it get deposited its loads here. Unfortunately in this area, this is from Ukimat close to Kedarnath, and we see that there are 2 villages called Mangli and Chunni in between, and then both of them were destruction was quite. So there were a few skeletons still buried here under the Mangli village that couldn't be recovered. This particular landslide is there since last 20 years at least. Um this is from the Barunavat Parvat in Uttarkasi area, and there had been a trifurcation, and from this trifurcation we can make out that how devastating this landslide had been. In list 4 image, our own list 4 image, ISRO's satellite, we can see that how the trifurcation beautifully has been captured. Now, what will be the input parameter? The input parameters can be the detail elevation model. First thing that you have to give input for any type of modeling is that this type of modeling is your digital elevation model. So DM has to be of high spatial resolution. Then we have to have some orthorectified image where you can get to know where the cracks are appearing. Then block area or release area, we have to identify an area where that will be released as a block. So basically on DEM you are encircling or making a polygon. You postulate that this is the spot where from the masses are going to move down. So if you let the software know the areal extent from, as because it is on a DEM, so each point it knows the height, so that is how basically it calculates the total volume. So total volume is known. Then the frictional value is very much important. We need to understand this. Suppose the red block is going to come down, so the mg sin theta is the force that is due to the gravity that is dragging the material down, and opposing is my friction, total friction. Why total friction? Because the debris contains rock and water, rock chunks and water. So the frictional forces due to rock and water will be separate. So that's how the total friction S is basically due to the friction due to my solid particles and due to my liquid material. So taken together gives me the total friction that is opposed against the mg sin theta. So the governing equation is that if this mg sin theta or gravitational pull is more than S, more than equal to S total friction, then the landslide happens and the material start dislodgement and it get deposited downstream, down the slope. So that is the basic principle. But before what the friction, total friction stands for, this is the governing equation that basically tells you how the total friction can be calculated. But what is behind this is two factors, this mu and xi. There are two frictional coefficient. One is for dry friction, that is for rocks, and this for the viscous turbulent friction, or xi, that is for the water phases or slurry. So we have to know about this. So there are ways that there are empirical models where from people have done this for similar situation and they have come up with some values that we can put similar situations. But there are ways that is available in engineering geology, and from instrumentally derived also we can get the mu and xi. These mu and xi, if you put in the equation, it can make the slide happen, or if the friction is that much, it will hold it. So that is how the model runs. This is the output of the model. Is source area we have identified as this, and this is how a debris flow looks like. At the source area, it is a torrent, sharp crested torrent, and then down there, whenever the slope is less, there is a platform it has deposited, and there is to be a village there. Now, except this house, all are gone. These are the results looks like. So maximum velocity, so the beauty of this model is that anywhere you click, you can get to know according to the scale what the velocity is. So the velocity, the maximum height. Now the road basically goes like this. So suppose if you want to know what is the velocity, what is the height that is available at the road crosscut. Road crosscut means where the debris flow meets the road. So why we need to know this? Because suppose we know that we're doing it for the predictive modeling, and we know that in next rainy season the landslide is going to happen. So what we will do, if it happens, how it will happen, the model can tell you. So if you know the total height at this juncture exactly, or this juncture where there is a crosscut between your road and the upcoming and then the sliding material, so at that point what will be the velocity? So if this velocity or this height is known priorly, we can construct a RCC wall or a dam kind of thing, so that the initial thrust of the material that is moving under the influence of gravity is digested by this wall. So what will be the height of this wall? The height of the wall should be more than the height of the material that is coming down with. The velocity is important because if the membrane, or if the wall, how much width of the wall has to be there. So with width, the cost of the wall increases. So we can make it wide, but then again cost goes up. So the optimum width of the wall basically is determined by the momentum or the velocity. So that's how we get to know the maximum momentum, maximum pressure. So all these factors, if it is known to us, it basically tells me that at each of the location how strong this debris flow is, and if we have to provide a remedy, if we have to provide a wall kind of thing, how strong it has to be made. So we get direct ideas from this. Similar results we have got from Uttarkasi, where if you remember there is a trifurcation that is beautifully depicted by our list for image. Now, has my model followed that exact trifurcation? We have modeled and then we've seen that they basically, with some exception, largely they follow the exact spatial extent that is available on the ground. My model follows exact the same torrent. Now if they are following the exact thing, then it means that they are right. Or suppose if they go somewhere else, then something has to do with the model, something has to do with the algorithm or your inputs. This kind of profile is also something that you can very easily get as output from the model. So if we know the 0 0, that means where from the debris flow started, it's going moving this way 800-meter distance suppose, and this is how the maximum velocity increases decreases. The maximum velocity has to come down to 0 at the point of deposition, and how the altitude also decreases. So this tri-axis basically you can get idea about the velocity, flow height, flow momentum, and pressure. There's one nice case study we'll end up with this discussion with is that we did in Kedarnath post 2013 event. We have seen that we have noted that it's generally framed like that. There's a lot of water, there's heavy incident rainfall. Those nights, I guess 15th or 14th June 2013. So because of the water, that much of devastation was there. But we have calculated the water was there, but it was not that much to wreak a havoc like this. So what else could be the cause? We have analyzed that the debris flow perhaps are more important. Analysis of debris flow are important. And why? Because the debris flow brings it lot of its load and deposit somewhere here. There are enormous landslides, there are enormous flows. I will show you the facts and figures. Then there is another flow. This is Kedarnath temple, and this is another flow, debris flow 2 coming like this. So if I have deposited my material here or here, what happens? The river that is coming like this, they are partially blocked or completely blocked. If they are blocked, they take a different path like this, and now they are forced to pass through the heart of the city. Unfortunately, with Kedarnath town, what happened there? There used to be a paleo channel already existing there, and water, when it blocked due to the debris, the water basically took a least resistant path through the. It activated the paleo channel, and it basically cut across the city, the town itself. Through the heart of the city, the water now flowed. Earlier it was flowing like this side. Right. So yeah, this is how in 3D it looks like. So this is my calculation domain. We call it green border is calculation domain. There are small water sets. Simply that we know that the flow will not will not go this side or this side. So within this gets restricted. And this is your release area. Release area means the source area. The result, if you look at it, I was trying to make you understand how big the debris flow or the landslide was. Please understand, debris flow 1, that is upstream of the temple, was of length 1.5 kilometers. So 1.5 kilometer the landslide material is coming down, and it is getting deposited. Its material on its path, and at the I mean where it meets the river at the bottom of the valley. Simulated maximum flow height is 4 to 6 meter and simulated velocity is 5 to 7 meter per second. So these kinds of figures are sufficient enough to block a river and to get it diverted. This is something happened in Malin in Maharashtra, close to Pune, and that also happened in 2013 or 14, maybe. The casualty was again around. We tried Malin modeling because we have done a lot of analysis in this part of Himalaya, northwestern Himalaya. We tried to see that with if we change the rock type, suppose we go to a basaltic terrain, whether my model works fine or not. We have seen that in basaltic terrain also like this, you can see the result and how beautifully it has been predicted. There is a notorious landslide called Kaliaso that happens close to this in Uttarakhand state only, close to Dehradun, and this photograph basically shows you the results where these are basically novice results. I call it novice because why? At the beginning, if somebody starts doing modeling, their product is going to cross the river and then it will get extended up to this. So generally it should not happen like this. So they will get restricted within this only. So with experience you can generate this kind of models and you can get to know the variation of spatial variation of height, velocity, pressure and momentum all around, right. This is the place Kaliasur I was talking about. So we took two resistivity sections also at the source area just to see that apparently they appear dry, but is a source of saturation there. We found that there are source of saturation very subsurface, and that perhaps could have been one of the reasons. One reason obviously is the undercutting of this bend. There's the inner bend of river Ganges, river Ganges, river Alaknanda, and then basically it cuts this point, and as because this cutting is going on continuously, so the landslide keeps on happening. But apart from that, we have at the source area also we found that there are some saturation zones at shallow surface. Next is how do I validate these results? It's very important that the mu and xi that we get from empirical models we give as inputs to the software, we see that whether the same thing we can get back from the instrumentally derived ones, and we have found that we go to field, collect samples, and at the same saturation level if we run our instruments, can we get the same mu and xi? We have seen that we get within the same mu and xi. This is one type of validation because if the values you are running your model, successfully running your model, these values are obtainable from your ground collected sample or no. So if they are matching, then that means your model is valid. So what after simulation? We have seen that the debris flow 1, the model height, momentum, velocity was that much. It's quite high enough to provide sufficient blockade of the main course of river Saraswati, that is Mandakini, and consequently it flooded the area. Numerical simulation flow modeling can be used for calculation of vital physical parameters. We have seen that. Shear strength parameters obviously is a good model, can be validated by laboratory instrument methods. Future flows can be predicted. In a big landslide, it happens that it's not as one time the landslide happens, keeps on happening every 2 years, 3 years, it comes back. So for those, basically, we have to keep our models ready. But there are limitations. We in this kind of models we didn't see that the numerical simulation derived models that neither consider the side channel contribution. So one big landslide is like this. So obviously nature generally happens sidewise also, it has some contribution. So that is not considered, or the assimilation of en mass en route erosion. So something is moving, it will erode en route also. So the product, the mass basically will be increased, but generally once I fix at the source area the same mass, it follows with. So that's a assumption, that's a basically limitation of this. And then simulated height and momentum, thus what we get are on the more lower end, more conservative, I will tell. So what are the take home points for this landslide? Is the concluding slide. We have understood that many of the landslides in northwestern Himalaya have a major debris flow component. So it's not as such a landslide, there can be the more dangerous one will be the debris flow, as because it contains a lot of water. Then the landslide hazard and liquefaction susceptibility mapping aided by Earth observation techniques, analysis of Earth engineering, geoengineering aspects had led to damage assessment till date. Comprehensive assessment of landslide hazard requires process-based modeling, what we have described in the second part of this lecture. Analysis and simulation and hazard mapping of major landslide and debris flow and liquefaction events, post factor and predictive both in the Himalaya had led to the derivation of important physical parameters. Of late, we have seen that leader based TLS or UAV based sensors, they basically create very high resolution DEMs. But please understand, if the DEM is of very high resolution, centimeter level spatial resolution, that again requires a very good software, very good system to process those. And future potential flows, obviously, as I have told, in vulnerable locations can be repeatedly modeled if the geology and topography is at par. Thank you so much for carefully listening to this lecture. Thank you for your patience. This photograph is taken from Sonprayag, where from now if you go to the Charyam, take the Charidham Yatra, and if you're proceeding towards Kedarnath, you have to, your vehicle will stop at this place, and this onwards you have to take either the local vehicle, or suppose you take a another type of pony or something like that, you start your trekking. So before 2013 event, Kedarnath event, this area used to be a gorge, deep gorge, but after 13, see the how much debris it has brought here. So it has become a football ground of expansion. It was earlier, it was a gorge like of thing. So thank you for your patient hearing.